All right, welcome everyone to the Week 6 Math 2419 Weekly Review. This one will be covering velocity, acceleration, and position vector valued functions. We'll also be going over tangent vectors and normal vectors, and lastly we'll talk about arc length and curvature. All right, so we'll go ahead and start. Position, velocity, and acceleration. This is just going to be a brief, since we did touch upon this last week. If we let r of t be a position vector, then we can say that velocity is the first derivative of that position, and acceleration is the second derivative of that position vector. And of course, we can say that speed is the magnitude of velocity, so that would be the magnitude of the first derivative. And for instance, if we wanted to do a really quick problem, let's say we wanted to find the distance find the distance traveled by a particle between t equals 0 and t equals 2, if its position is r of t equals to 1/2 t squared, 1/3 t cubed. All right, so the distance traveled would be the integral of the speed. So we can write that out. D equals to integral from time t equals 0 to time t equals 2 of the speed, which is the magnitude of the first derivative. Now that's the integral from 0 to 2. If we take the first derivative, r prime of t, that is equal to 1/2 times 2t gives us t, 1/3 times 3t squared gives us t squared. So our magnitude of that vector is t squared plus t to the 4th dt. And if we factor out a t squared, it's the integral from 0 to 2 of t square root 1 plus t squared dt. Now we can solve this by using u substitution. If we let u equal to 1 plus t squared, du is equal to 2t. So we get that our d is equal to the integral of 1/2 square root u du. And that gets us to 1/3 times 1 plus t squared to the 3/2 from 0 to 2. And I just substituted my u back out and integrated all in one step. And when we plug in our limits of 0 and 2, get 1/3 times 5 to the 3/2 minus 1 as our final answer. But again, the important thing to know here is know that position is the integral of velocity, so velocity is the derivative of position, acceleration is the derivative of velocity, and speed is the magnitude of your velocity. All right, that'll be it for the velocity and acceleration portion. You can always look back at last week's review as well if you want to do a bit more in-depth review of it. Next, we'll take a look at some tangent vectors and normal vectors. There are a couple of important vector components. So let's say that we have r of t, and it is a vector valued function. Well, then there are two vectors called the unit tangent vector and the unit normal vector. And basically, if our R of t curve looks something like this, then at any given point, we can say there is a unit tangent vector and a unit normal vector. And these will be perpendicular. The unit tangent vector is parallel to our vector valued function, and the unit normal is, well, normal or perpendicular. And the way we can find these is, well, with the tangent vector, it's pretty simple. The first derivative, as we know, gives the slope or a tangent vector at the specified point. So in order to find a tangent vector, we just take the first derivative, and in order to make it a unit vector, we simply divide by that vector's magnitude. So that's how you find a unit tangent vector. For example, if we wanted to find the unit tangent of R of t equals to e to the t comma t, well, we can really easily find our first derivative, which is e to the t comma 1, and then the magnitude of that first derivative would be equal to square root of e to the t squared is e to the 2t, and then 1 squared is 1. So our tangent vector, we can write it either as e to the t over square root e to the 2t plus 1, comma, that should be a 1 over square root e to the 2t plus 1. And remember, this is just my first derivative divided by the magnitude of the first derivative. Alternatively, I can pull out my whole magnitude of a first derivative, write it as 1 over square root e to the 2t plus 1 times e to the t comma 1. So the unit tangent is easy enough. The unit normal is similarly defined, actually, but this time we define the unit normal vector in terms of the tangent vector. We say that the unit normal vector is the first derivative of the unit tangent divided by the magnitude of the unit tangent vector. The reason being is if you take a unit vector and take the derivative of a unit vector, you will always get a vector that's perpendicular to your original vector. The reason being, it comes from a proof involving the dot product. I won't go into that right now, but it is a helpful little fact to know. So let's go ahead and do an example where we find the unit normal. Find the unit normal vector of this function R of t is equal to 2t comma t squared. Well, first off, we know that in order to find our unit normal vector, we need to find the unit tangent. And in order to find the unit tangent, we need to take the first derivative divided by the magnitude of the first derivative. And our first derivative, r prime of t, is equal to 2 comma 2t. So our unit tangent would be equal to 2 comma 2t divided by the square root of 4 plus 4t squared, which is equal to 1 comma t over square root 1 plus t squared. All right. And I'm going to go ahead and write that component-wise, I suppose, without a coefficient out front. So we have t of t is equal to 1 over square root 1 plus t squared, comma, t over square root 1 plus t squared. All right, and now we know that the normal is the first derivative of this tangent vector divided by the magnitude of that first derivative. So t prime of t is equal to, in this case, the derivative of this first component would be, we have 1 plus t squared to the minus 1/2. So we have minus 1/2 times 1 plus t squared to the minus 3/2 times the derivative of the inside, so times 2t. Then on the second portion, we have to use the quotient rule. We say low times the derivative of the high portion, 1 plus t squared times 1 minus high times the derivative of the low portion. Derivative of the square root of 1 plus t squared is 1/2 times 1 over square root 1 plus t squared times 2t, all over the bottom portion squared, so all over 1 plus t squared. And if we wanted to simplify this a bit, that simplifies down to, that 2 cancels with that 2. We end up with negative t over 1 plus t squared to the 3/2, comma, this is, I'm going to go ahead and multiply this final portion, the second component, by square root 1 plus t squared over square root 1 plus t squared, in order to make sure that we don't have any fractions in the numerator like we do right here. So square root 1 plus t squared to square root 1 plus t squared gives us 1 plus t squared. This 1 plus t squared cancels with that 1 plus t squared. This 1/2 cancels with a 2. We're left with minus t squared right here. And on the denominator, we have 1 plus t squared times square root 1 plus t squared, which gives us 1 plus t squared to the 3/2. And if we further simplify that, we can go ahead and pull out a 1 over 1 plus t squared to the 3/2 as a coefficient. On the inside, we're left with a minus t, and then t squared minus t squared, those cancel, comma 1. Now, in order to find the magnitude of this, since we already have a coefficient out front, we don't necessarily have to multiply that back in. We can just say that is going to be a part of our magnitude. So that would be 1 over 1 plus t squared to the 3/2, and then we multiply by the magnitude of this vector, so times square root 1 plus t squared. And as you see, this simplifies down to 1 over 1 plus t squared. Just double checking all my work here. I don't think I made any mistakes. If you do see something, just call me out on it. Let's see. So we started out with, got our unit tangent, and that looks good. So, all right. Perfect. Now our unit normal is of course equal to our unit tangent, or sorry, the first derivative of our unit tangent divided by the magnitude of that first derivative. So we have 1 over 1 plus t squared to the 3 halves times this vector minus t comma 1 all over 1 plus t squared. Okay, and this simplifies down to, we can take this 1 over 1 plus t squared to the 3 halves, move it down to the denominator. As a final answer, we get 1 over 1 plus t squared to the 5 halves times negative t comma 1. And I am pretty sure that's correct, if you've been following along. And notice a mistake, sorry about that. But you get the general idea. All right, any questions? Okay. In that case, I'm going to go ahead and give you a practice problem, or a couple of practice problems. This first one, find the unit normal of this function r of t, this helix equals to sine of t cosine of t. Or I guess that's just a circle. Secondly, find just tangent vector of this function r of t equals to sine of t e to the t. And I'll give you a couple of minutes to work that out. All right, how's it coming? Right, let's just go over this first one. So in order to find the unit normal, we need to start by finding the unit tangent. And in order to find the unit tangent, we need to find first derivative over the magnitude of the first derivative. In this case, the first derivative is going to be cosine t negative sine t. And this is already a unit vector because we would get the magnitude being cosine squared plus sine squared, which is of course 1. So we have our tangent vector minus sine. Now our unit normal is going to be the first derivative of the tangent over the magnitude of that first derivative. And in this case, the first derivative of the tangent vector is equal to negative sine t, negative cosine t. And if we take the magnitude of this vector, we see that once again, it's already a unit vector as well. So this would be our unit tangent vector. Just like that. Make sense? All right. Next, on to the second question. Find the unit tangent vector of sine t e to the t. Of course, we know that the unit tangent vector would be r prime of t over the magnitude of r prime. In this case, r prime of t is equal to cosine of t e to the t. So then the magnitude of r prime of t would be equal to the square root of cosine squared t plus e to the 2t. And we can't really simplify that at all, so we would write that our tangent vector is simply equal to 1 over square root cosine squared t plus e to the 2t all times cosine of t e to the t. All right, there is one last thing to discuss with tangent vectors and unit normal vectors. So this also brings in a bit of velocity version. So let's say we have a position vector r of t, and we know it has a normal, unit normal vector, n of t. Well, then we can write the acceleration vector as follows. The acceleration vector would then be equal to some tangential velocity times the unit tangent plus the normal velocity times the unit normal. And this, of course, just kind of makes sense. We're basically just saying if we have these two vectors, the unit tangent and the unit normal, well, all we need to know is the magnitude of the velocity in the tangential direction and the magnitude of the velocity in the normal direction. And with those things together, we can write our acceleration. But in order to find these a sub t and a sub n, the tangential acceleration and the normal acceleration, those take a couple of formulas. And one thing to note, a sub t and a sub n, your tangential acceleration and normal acceleration, these are scalars, not vectors. So these are just basically constants. Well, not constants, but numbers rather than vectors. Your tangential acceleration is going to be the derivative of the magnitude of your velocity. And your normal acceleration is going to be equal to the magnitude of your velocity times the magnitude of your derivative of your tangent, unit tangent. It's also going to be equal to the magnitude of velocity crossed with acceleration over the magnitude of velocity, or the square root of the magnitude of acceleration squared minus your tangential acceleration squared. And these are just a couple of handy formulas to know. I don't have any examples with these, but these do crop up occasionally. So there are the formulas to use. Now, there is a bit more to cover, arc length and curvature, and that's really what I wanted to focus on in this section, this review, because those tend to crop up a bit more frequently in class. All right. So we covered arc length with a few other methods or types of functions, such as just regular rectangular. You covered it with parametrized functions and polar functions. And now we're going to cover arc length, a vector valued function. So if you have a vector valued function r of t, well then its arc length is going to be equal to, we denote arc length by using s. It's the integral from some starting t value to some ending t value of the magnitude of your first derivative. For instance, if we wanted to calculate the length of cosine of t, sine of t, t on t equals 0 to t equals 4, you could set that up by saying the arc length, the integral from 0 to 4. Our first derivative would be negative sine t cosine t 1. So the magnitude of that would be the square root of sine squared t plus cosine squared t plus 1 dt, which is the integral from 0 to 4 of root 2t, not root 2t, sorry, just square root of 2 dt. And of course, that comes out to be the square root of 2 times d from 0 to 4, which gives 4 square root 2 as our arc length. Now that wasn't a super hard problem, but basically that's how you kind of plug in the general, that's how you basically use the formula. There is, using this definition of arc length, we can define something called the arc length function. There we go. And this is a function of t, and all it is, it's going to be the arc length from some starting position. It's frequently 0, so that's what I'll use here, but it could be any number. That's important to note. That could be 7 or negative 10. Basically any number is just commonly 0 to some value t. T is your variable here. And then it's simply the arc length of your function. Of course, we can't have t as both a limit of integration and something and the integrand. So we have to replace the integrands with u's. But this is how the arc length function is defined. And using this arc length function, we can say that there is something called the arc length parameter. And this is a special kind of, this is basically, the arc length parameter is essentially a variable. It's also denoted by s, so that when we plug in that variable instead of t in our original vector valued function, the magnitude of the first derivative would be equal to 1. Or in other words, it has a constant speed. In other words, if we let s be the arc length, of our vector valued function r of t, then this arc length is a function of t, like we see using the arc length function. Then we can say that when we take this function of t and plug it in to our vector valued function, that is the arc length parameter. Now, I'm going to go ahead and do an example because definition is a bit confusing if you're just looking at it. I think an example can really help clear things up. So let's say the example is find the arc length parameter of r of t equals to t cubed, comma, negative 4t squared. All right. Our arc length function would give us the integral from 0 up to t. I'm just finding the arc length function here of the square root of the magnitude of the first derivative. So first derivative, r prime of t, is 3t squared negative 8t. So the magnitude of that would be the square root of 9t to the fourth plus 64t squared dt. Of course, since we have a t as a limit of integration, all of our t's on the inside should be replaced by u's. So that would be a 9u to the fourth plus 64u squared. All right. Now we can go ahead and take out a u squared from the inside. So that's the integral from 0 to t of u square root 9u squared plus 64 u. We're going to be doing a u substitution to solve this. Of course, since we already have a u in there, I'm going to use a different letter v, and I'm going to let it be the most complex part. So then dv u dv is equal to 18u du. So in order to substitute out this u du, we replace it with a dv over 18. So then s is equal to the integral from 0 to t of 1 over 18 v to the 1/2 dv, which is equal to the integral of v to the 1 over 18 v to the 1/2 gives us 2 over 18 times 2 over 3 times 9u squared plus 64 to the 3/2, all from 0 up to t. I went ahead and substituted my v right back out. All right. I'm not quite sure where this 2 came from right here. That should be a 1 over 18 still. Yep. Okay. All right. Now when we plug in our t and our 0 as our limits of integration, we would get that s is equal to, in this case, 2, that should simplify to 9 and 1 over 27 times 9t squared plus 64 to the 3/2 minus 1 over 27 times 64 to the 3/2. Now if we continue to simplify that down, 64 to the 3/2 would give us 8 to the 3rd. So s is equal to 1 over 27 9t squared plus 64 to the 3/2 minus 8 cubed. All right. So this is our arc length function. In order to find the arc length parameter, we need to find s in terms of t. So right now we have, we need to find t in terms of s. Right now we have s in terms of t. We need to flip this function around and isolate t. So in order to do that, we'll start by multiplying both sides by 27. I'm going to start writing my s's in cursive so you can tell them apart from 5s. 9t squared plus 64 to the 3/2 minus 8 cubed. Now continuing onward, we add 8 cubed to each side and then raise each side to the power of 2/3. We end up with 27s plus 8 cubed to the 2/3 is equal to 9t squared plus 64. So we subtract 64 from each side and then divide by 9. We get 27s plus 8 cubed to the 2/3 minus 64 all over 9 is equal to t squared. Next, take the square root of each side. We get t is equal to the square root of 27s plus 8 cubed to the 2/3 minus 64 all over 9. And our arc length parametrization would be r of t, where t is equal to this function of s. So we can say that our arc length parametrization, r of s, is equal to, because r of t was equal to t cubed negative 4t squared, r of s would be equal to 27s minus plus 8 cubed to the 2/3 minus 64 all over 9 to the 3/2. That's because I combined the square root and the to the 3rd power, comma negative 4t squared. So negative 4 times 27s plus 8 cubed to the 2/3 minus 64 all over 9. And you might be thinking, why did we go through this big long process to make a function that looks even more complicated, that looks way more complicated than our original one? Well, the Arclength parametrization has a couple of advantages. The main one is it has a constant speed. So what that means is if you want to know the arc length when s is equal to 7, well, the arc length is equal to 7. Basically, it moves at exactly the same rate as your arc length increases. So r prime of the arc length s, the integral of that first derivative from 0 to some value t, would be equal to exactly whatever value you went to. So if you wanted to know the arc length from 0 to 4, where s is equal to 4, it would just be 4, and of course it has constant speed. A couple of pretty big advantages there. If you have any questions about it, feel free to ask. If you don't have any questions, though, here's a practice problem. It's not quite as algebra heavy as the last one. In fact, I tried to make it considerably less algebra heavy. So find the arc length parametrization of this function r of t is equal to sine t cosine t, this helix. And I'll give you a couple of minutes to work on that really quick. All right, let's go ahead and go over this one really quick. So remember, the first step to finding an arc length parameterization is always to find your arc length function. So our arc length function would be the integral from 0 to t of the magnitude of the first derivative. In this case, our first derivative, r prime of t, is equal to cosine of t negative sine t 1. So the magnitude of that would be integral from 0 to t the magnitude is cosine squared plus sine squared plus 1 is 2. Take the square root of that, root 2 du, and of course that gives us root 2u from 0 to t. And of course that's square root 2 times t. We simply take our arc length s and set that equal to the square root 2 times t, then isolate t by itself, which is easy. We just divide both sides by square root 2, and we get t is equal to the square root of 2 over s. All right. Lastly, all we need to do is find r of t when t is equal to the square root of 2 over s. So then r of s would be equal to, oh dear, it should be s divided by the square root of 2. That's what it should be. Flip things around. So we say that r of s is equal to cosine of s over root 2. Oh, sorry, that should be the sine. Mixing up my first and second derivatives here. The sine of s over root 2 comma cosine s over root 2 comma s over root 2. All right, and as you can see, if we took the first derivative, we would get cosine of s over root 2 times the derivative of the inside is 1 over root 2 cosine s over root 2, negative 1 over root 2 sine of s over root 2, and lastly 1 over root 2. And if we took the magnitude of this, we could see that would give us square root of 1/2 cosine squared plus 1/2 sine squared plus let's see, where did I go wrong here? Oh, plus 1/2. Of course, I was right. 1/2 cosine squared plus 1/2 sine squared is of course equal to just 1/2. Square root 1/2 plus 1/2 is equal to 1, and it has a constant speed. But your answer would be this r of s right here. And just to recap the process we took, all we did, first we found our arc length function, and once we found our arc length s in terms of t, we found then the reverse, t in terms of s, and replaced all of the t's in our original vector valued function with this arc length parameterization that we found. All right, so that is the arc length parameterization. The last thing we need to talk about today is curvature. And as the name suggests, curvature is basically a measure of how quickly a curve bends. Now there are several different formulas for curvature. We'll start with one for an arc length parameterization. So if r of s is an arc length parameterization, I'm just going to abbreviate it like this, and it's an arc length parameterization if the magnitude of the first derivative is equal to 1, then the curvature, k, represents curvature, is equal to the magnitude of the derivative of the tangent vector. I will say I very rarely use this function or this equation to find curvature, simply because the next one is applicable to a lot more functions. So if r of t is any vector valued function, and that, of course, includes all of these arc-length parametrizations. Then we can say that the curvature k is equal to the magnitude of the first derivative crossed with the second derivative all over the magnitude of your first derivative cubed. Another way to write this is the first derivative of your unit tangent, magnitude of the first derivative of your unit tangent all over magnitude of just your first derivative. But this first function right here, I would recommend memorizing. I use it basically for all of the curvature calculations. And lastly, there is a way to find curvature of a non-vector value function. If you have y is equal to f of x as a function of x, well then your curvature is going to be the absolute value of the second derivative of y all over 1 plus the first derivative of y squared raised to the 3/2 power. And this one is also probably good to know. I have seen it a couple of times in Math 2419. So just know that this one's there. This second one, though, is probably the biggest one. So let's do one quick example, and we'll see. Find the curvature of this function r of t equals to sine of t, cosine of t, and t. Well, your first derivative is going to be cosine of t negative sine t 1. Your second derivative is going to be negative sine t negative cosine t 0. So then r prime of t crossed with r double prime of t is going to be equal to cosine of t comma cosine of t times 0 minus 1 times negative sine of t gives us positive sine of t. Flip the signs into the second term, gives us negative sine of t. For the third term, we have cosine times negative cosine gives us negative cosine squared minus negative sine times negative sine. So we have negative cosine squared times negatives plus negative sine squared gives us negative 1 as our final component. Then if we take the magnitude of that, well, that is the square root of cosine squared plus sine squared plus 1, which is 1 plus 1, which is square root of 2. Right. And of course, we need the magnitude of our first derivative, which is square root of cosine squared plus sine squared plus 1, which is 1 plus 1, which is square root of 2. And our curvature is equal to the magnitude of the first derivative crossed with the second derivative all over the magnitude of that first derivative cubed. So that would be the square root of 2 all over the square root of 2 to the third, which is 1 over square root 2 squared, which is, of course, 1/2. All right. I'll go ahead and give you one practice problem, and then we'll call it from there. Find the curvature of r of t equals to t squared t cubed. I'll give you a couple minutes to do that. Alright, let's go ahead and go over this practice problem. Remember, once again, our curvature is going to be the magnitude of the first derivative crossed with the second derivative all over the magnitude of the first derivative cubed. So in this case, our first derivative, r prime of t, is equal to 1, 2t, 3t squared. Our second derivative is equal to 0, 2, 6t. So then r prime crossed with r double prime is equal to 2t times 6t gives 12t squared minus 2 times 3t squared. 12t squared minus 6t squared is 6t squared. Then we have 0 times 3t squared minus 1 times 6t, so negative 6t. And 1 times 2 minus 0 times 2t is 2. So then the magnitude of that would be the square root of 36t to the fourth plus 36t squared plus 4. And of course, the magnitude of our first derivative, r prime of t, is equal to the square root of 1 plus 4t squared plus 9t to the fourth. Not a whole lot we can do to simplify these, so we can basically just write out our curvature as being, I'm going to go ahead, the only simplification we can do is pull a 4 out of the numerator, so 2 square root 9t to the fourth plus 9t squared plus 1 over 1 plus 4t squared plus 9t to the fourth to the 3/2. And that would be our answer. Anyway, thanks for coming to this review, and have a nice day.